Hello, yeah, we're carrying on with circular motion questions in this video, and this is one of the experiments that I just can't stand in A-level physics. I just don't think it's very good at all. But they seem obsessed with it in exam questions and in A-level practical, so we might as well have a look at it. This is the one where you've got this bung that you're swinging around in circular motion in a horizontal circle, and you've got this wire or this string which is going through a tube that you're holding, and we're trying to keep these masses in equilibrium, which is going to tell us what the tension in the wire is, because that's going to, or the tension in the string, because the tension in the string will have to be the same as the weight of the masses if we're going to be keeping the masses in equilibrium. The trouble is you can't really swing these things horizontally. You can't keep the radius of the circle constant. It's just nigh on impossible to actually do it. And the payoff in order to do it all is to work out the mass of the bung. Well, just stick it on some scales. What is the point of doing an experiment that doesn't work in order to work out something that you can just stick on some scales? It's just nuts. So we'll get on to more about that in a minute of me complaining about it. But we'll start off by drawing an arrow labelled F on the diagram to indicate the direction of the resultant force on the bung, right? So if the bung's going in a horizontal circle, then there's no vertical component. All we've got is the force towards the center of the circle. So we've got this horizontal line, which is going to be F towards the center of the circle, which you should note is not going to be parallel to the string, because the string has to have a vertical component of the tension to counteract the weight of the bung. So the string is not horizontal, but the circle that the bung is moving in is horizontal. All right, explain how the speed of the bung remains constant even though there is a resultant force acting on it. Right, there is, there's no component of the resultant force in the direction of motion. So you're only getting work done on the bung if there's force acting in the direction of motion, which there isn't at all. It's all perpendicular. So the force is perpendicular to the motion. So there's no work done. That's what we've got happening there. Right, now they try to carry out this experiment, probably with not much success, to investigate the relationship between the force F acting on the bung and the speed V for a constant radius. Right, describe how they obtain the values F and V. So there's a number of things that we're going to have to do here. So we've got to get the weight of the masses. So we're going to do our usual things. So we're going to do weigh masses using scales. Then we're going to have that the tension is equal to the weight of the masses. So yeah, that tension is going to be equal to W. That is F. So we've got that straight away. So when we're spinning this around, we need to say that we have to try to keep the masses in equilibrium and the circle horizontal and the radius constant, none of which anyone is going to be able to do with any significant accuracy. So we need to have all of those. And then we've got, we're going to work out how many, so time using a stopwatch again, so stopwatch, so we can time a number of rotations, time n rotations. So let's say we want to have a fairly high number, so we say n, I don't know, greater than 20, something like that. And then we can say 2 pi r n, so that is the distance over the time, is going to be equal to the velocity. So that's fine. So we're doing all the usual stuff. The things that we're measuring, oh, we need to measure r as well. So that's another thing we have to put in. So measure r using a ruler when it's stationary. So we've got this mark that they have on there, the reference mark That's what we're trying to maintain, which again, no one can really ever do. So yeah, it's just rubbish experiment. So all the usual things are the things we're going to measure, what we're using to measure it, and then we need to do a lot of rotations here. And then so we're averaging those out because it's going to be very difficult to just do this off of one rotation. Sketch on figure 3.2 the expected graph of f against v squared. So we've got f equals mv squared over r. That's our Newton's second law with the acceleration that we get in circular motion. So we're going to have a straight line through the origin where the gradient is equal to m over r. Explain how the graph can be used to determine the mass of the bung. Well, there we go. It's the mass of the bung is the gradient times the radius of the circle. Here, all that effort to work out mass of the bung. Yeah, what a waste of time. And you probably won't even get a very good answer for it. It seems with this that the thing that you can't really work out, I don't know, maybe you're better off if you're doing something about working out the force. You could work out the tension in the string. You know, if you fix the string at the end of this tube, then R immediately becomes fixed. So you've got a lot of certainty over what R is. So that's fine. You can still do the calculation for the velocity. I mean, it's the tension in the wire, the string that we don't really know. You can measure the mass. You can measure the radius. I mean, these are things that you want to deal with much more accurately, I would have thought. And then have an experiment for working out what the force is going to be. And then maybe you can have, well, how fast can you swing the bung around before the string is going to snap? You know, it's just, this whole setup just seems stupid to do an experiment that doesn't work in order to work out something that you can just measure anyway. So yeah, I can't stand this thing, but it comes up time and time again, so it's worth looking through it. Fortunately, it's relatively straightforward. So there's not much to get confused about on all of this. It's just another one of practicing our experimental answers where we're going through how do we do this practical. Well, hopefully this question will be a bit better. We're starting with a couple of definitions. We've got state Newton's first law of motion, which doesn't come up as much as the others. So that is that an object remains at rest or moving at a constant velocity unless acted on by a net external force. So remember with that, that's not just saying, you know, this is how an object behaves. It's also saying that in Newtonian classical mechanics, it's only forces that's changing the motion of an object. It's only forces, nothing else will do it. So that's often overlooked in the definition. But yeah, we're just saying constant velocity or at rest unless acted on by an external net force. Define the Newton. So the Newton is the force required to accelerate 1 kilogram mass by 1 meter per second squared. So nice starter on those. Now we've got another jet plane. We've got jet planes everywhere. On the deck of an aircraft carrier, accelerated before takeoff using a catapult. The mass of the plane is that, accelerated from rest to a velocity of 55 meters per second in a time of 2.2 seconds. So what is the mean acceleration of the plane? That is going to be 55 divided by 2.2. Okay, so 2.2 is, what is that, 11 over 5. So we're going to have 25 is going to be that, isn't it? 25 meters per second squared. Yeah, the distance over which the acceleration takes place. So the distance is going to be the average velocity multiplied by the time. So it will be 55 times 1.1, which is 60.5 meters. Yep, so we got that. Well, 61. I was just checking for significant figures. So 61 meters. The mean force producing the acceleration. So we've got our acceleration there. So our average force is going to be the mass times the acceleration. The mass is quite big. What was it? 3.2 times 10 to the 4. 3.2 times 10 to the 4 multiplied by 25. So what is 3.2 times 25? That's 7580 times 10 to the 4. So 8 times 10 to the 5 newtons. Right, that's dealt with B. The jet plane describes a horizontal circle of radius 870 meters flying at a constant speed of 120 meters per second. State the direction of the resultant horizontal force acting on the plane. So that will be towards the center of the circle. Towards center of circle. Always the same with these. Calculate the magnitude of this horizontal force. So again, we're doing F equals ma, but now we know it's for a circle. So it will be mv squared over r. M 3.2 times 10 to the 4 multiplied by v squared, 120 squared, divided by 870. Right, okay, I'm going to go to the calculator this time. It just seems a bit much to do just on pen and paper. 120 squared divided by 870 is that times 3.2. So we got 53 times 10 to the 4. 53, so 5.3 times 10 to the 5 newtons. So yeah, at least it's, well, yeah, that was easy enough to work out, I suppose. Right, and now by changing the velocity of the plane, it can be made to fly in a vertical circle of radius 1500 meters. At a particular point in the vertical circle, contact force between the pilot and his seat may be 0, and the pilot experiences, in inverted commas, weightlessness, something we've spoken about many times before, because of course he's not really weightless, not if you're using our usual theoretical definition of what weight is. It might be different if you're using the operational definition, but usually we're not. State and explain at what point in the circle this weightlessness may occur. So it will be at the top of the circle where the weight provides the required centripetal force. Centripetal force. Okay, calculate the speed of the plane at which weightlessness occurs. So it will be where the weight is the centripetal force. So the weight of the plane, where are we? 3.2 times 10 to the 4 g. That will have to be equal to our mv squared over r. So that would be equal to 3.2 times 10 to the 4. So you can see how these are all going to cancel out. Times v squared. That's what we're trying to work out. Over, so what was the radius? 1500 meters. So we can cancel those. So v is going to be the square root of 1500 g. So 1500 times 9.81 is that. Square root it, and we've got 121 meters per second. So 120 meters per second, two significant figures. Yes, a lot of calculations in that. That was a bit more interesting than the last one. Although fairly standard calculations, but it's still, nice to go through the process. Right, now we're stepping onto the London Eye here. We've got 32 capsules equally spaced around the edge of a large vertical wheel, radius 60 meters. Wheel rotates about a horizontal axis such that each capsule has a constant speed of 0.26 meters per second. Calculate the time taken for the wheel to make one complete rotation. Okay, so velocity, distance over time. What we're trying to get the time. So we want to have distance over velocity. So the time is going to be the distance, which is 2 pi r, 2 pi times 60, divided by the velocity, which is 0.26. Right, so type away. 120 times pi divided by 0.26 gives us 1,450 seconds. 1,450 seconds. We've only got two significant figures again, so 1,500 seconds to two significant figures. That's that one. Each capsule has a mass of 9.7 times 10 to the 3. Calculate the centripetal force which must act on the capsule to make it rotate with the wheel. So that would be mv squared over r. What we got here? So 9.7 times 10 to the 3 multiplied by 0.26 squared divided by 60. Right, that's not going to be a very big number. 9.7 times 0.26 squared divided by 60 is 0.0. We've got this 10 to the 3 still come in, so it'll be 10.9. 10.9, which is 11 newtons. Again, to our accuracy. All right, now we're onto the drum of a spin dryer with a sock in it. The dry sock is shown on the inside surface of the drum. Okay, draw arrows on figure 2.2 to show the direction of the centripetal force acting on S when it's at points A, B, and C. Oh, well, it's just going to be lots of arrows drawn towards the center of the circle. State and explain at which position A, B, or C the normal contact force between the sock and the drum will be the greatest and least. Right, so the greatest is going to be at C because the centripetal force is constant. Therefore, the reaction force, normal contact force they've called it, so normal contact force must counteract the weight, whereas you're going to have the opposite on the other side. If we're at A, it will be the least because the normal contact force just has to add to the weight. Contact force adds to weight for centripetal force. Yeah, run out of space, but there you go. So yeah, that's a much more straightforward question. But yeah, all of these, it comes back to this idea that you have to keep on stressing and think about with a circular motion, that the centripetal force is not a force on its own. It's just a category. It's just a description for whatever it is that's providing that force towards the center of the circle. So the centripetal force, what it is that's creating it, is going to vary around this circle. If we're at B, it's just the reaction force because the weight is acting downwards. We've just got reaction force towards the center. If it's at A, it's the reaction force plus the weight. If it's at C, then the weight is acting against the centripetal force. It's just the reaction force which is providing it. So what is actually providing the centripetal force changes. There is not an additional force. It's just the label we're giving to whatever it is that's creating the circular motion. Sometimes people get a bit confused about that.